name's Donato. We're working on problem number 97 from chapter 15. Let's start off by reading the problem. Common aspirin is a salicylic acid, which has a structure shown here and a pKa of 3.5. Calculate the pH of a solution in which one normal adult dose of aspirin, 6.5 times 10 to the second milligrams, is dissolved in 8 ounces of water. A couple things to point out is a pKa value of 3.5 indicates that we'll be working with a base of 10 in order to eliminate the log value associated with the 3.5. We're dealing with a weak acid, which means we don't know how much it will dissociate, and we need to find that out using a Rice table. Units are in milligrams and ounces, so appropriate conversion rates will be needed. And the first step is to find the initial concentration of salicylic acid in order to conduct the Rice table. A couple more important values and conversions to note. 1 fluid ounce converts to about 29.57 milliliters, and the atomic mass of salicylic acid is 180.158 grams per mole. This will be useful from converting from ounces to then eventually get to moles. As mentioned earlier, the base 10 approach in this case allows us to find the X value inside of the log, which will give us the Ka value. The Ka value turns out to be 3.16 times 10 to the negative 4. When converting from ounces to milliliters, it is then important to convert to liters again, since we always work with liters mostly over milliliters. We end up with about 0.24 liters. When we convert from milligrams to grams, that's a pretty straightforward conversion, and we end up with 0.65 grams, which is then useful alongside the atomic mass of salicylic acid to then find the amount of moles we're working with. With the moles, we can then proceed to find molarity, which is equivalent to concentration. Because we have moles and we have liters, we now have 1.52 times 10 to the negative 2 moles of Because acid. We found the concentration of our acid, we can now move forward with our Rice table. As we've mentioned, 1.52 times 10 to the negative 2 is the initial concentration of the salicylic acid. Pure liquid like water does not get mentioned in the Rice table. And our products, our initial point, there is none. So we begin with no products. Because our reactants will be used up, we will lose some reactants and we will gain some amount of product. Because the concentration of H plus ions is equivalent to products or reactants, and we know that that's equivalent to our Ka value, we can then use the quadratic formula to find our X value. In this case, we need to do some distribution and multiplying to the other side in order to appropriately get our A, B, and C values. In this case, our A value is 1, our B value is 3.16 times 10 to the negative 4, and C is negative 4.82 times 10 to the negative 6. These values are very important for the quadratic formula, which is the next step. Because we outlined our A, B, and C values, the quadratic formula at this point is mostly plugging in. We have a negative B value here of negative 3.16 times 10 to the negative 4, plus everything under the radical of B squared, 3.16 times 10 to the negative 4 squared, minus 4AC, A being 1, C being a negative value of 4.82 times 10 to the negative 6, all over 2. We get an X value. And we know that by taking the negative log of the concentration, we can end up with the pH, and the pH is what we want to find ultimately for this problem. We end up with a pH value of 2.7. Ultimately, our problem asks us to find the pH of a solution. But in order to get to solving for pH, which requires a Rice table, we first needed to convert some units to their adequate counterparts, such as grams and moles, as well as liters. We took the approach of doing a Rice table, finalizing it with the quadratic formula to find the concentration of H plus after the balance equation had taken place, and finally doing negative log of our concentration to then find the pH values, which is what we needed to find in the problem.